Hi guys, welcome to my presentation about edge computing. So I'm going to jump right into an introduction. So first I'm going to start by defining edge computing, and on the right I found two definitions from a couple of my sources that I thought were really good for this. The first one I'm just going to read. It says edge computing directs computational data, applications, and services away from cloud servers to the edge of a network, which is the reason it's called edge computing. So what that basically, in summary, what that's saying is that it's taking some of the responsibilities that would have previously been handled maybe by the centralized cloud, so like one of the big GCP data centers, and it's moving it closer to end users. So it's moving it to the closer to the edge of the network, which is going to be closer to people that might be using it. So the next definition I got from a LinkedIn Learning that I watched that was really good about edge computing. It says ultimately it's a way that we're able to leverage a distributed architecture that is decentralized, but is able to also leverage the resources of some sort of centralized service, such as a public cloud. So I thought this one was a really good quote because it illustrates how edge computing really exists between like the main centralized cloud and the end user. And it's able to kind of have the best of both worlds in the sense that it's still part of the cloud, because you're still contacting, obviously, like computing power that is not local to your machine or your device or your IoT sensor. So you are using a cloud, but it's a little bit faster, lower latency, and we'll see a lot of the advantages later. So this was just a diagram that I thought was good that was from one of my articles, and it sort of shows a bunch of different examples here, but you see those little bubbles that say Edge Cloud next to each one. So obviously, like these different applications could contact the Edge Cloud first to do maybe some of the computing, maybe some data pre-processing before communicating then with the centralized cloud to either store or do further processing on that data. So characteristics of edge computing, I've just listed a few here. The first is dense geographical distribution. This basically just refers to the fact that in an edge network, there is a lot of different edge devices because especially for something like if you think about mobile, you want to have a lot of these available so that when people are moving around, they'll be within one that's pretty close that can so the latency will be pretty much the same no matter where they are. So you want to distribute these in such a way that you're kind of maximizing performance for people. We'll talk about that in our use case slides later. And then also mobility support, it kind of goes into that as well. I listed there Lisp, which is the location ID separation protocol, and this is important because mobile edge computing, or MEC, is the abbreviation for that, is a really, really big use case. This just basically means that because a lot of devices that are often using edge computing are mobile devices, you have to be able to separate the device's identity. So like I am device XYZ, you have to separate that from the location. You can't have them tied together because those devices are going to be moving around a lot. And that's kind of what the Lisp protocol does. So if you're defining an edge network that's going to be used by mobile devices, that's something you have to keep in mind. So next I have low latency, which is really the big advantage and the reason why edge computing has come into existence at all. So an edge node is physically closer to the end user, which I've mentioned. So the latency, the round trip from the user's device or the sensor or whatever to that edge node is just going to be lower than it is probably unless you live right next to a data warehouse for GCP or something. So you can do like near real-time computation using an edge network. The last thing on there is heterogeneity, which is there's no one platform technology or architecture for edge computing. There are a lot of different protocols, a lot of different providers for this. As of now, there's no like really big standards in place. It's kind of a cutting edge field. It goes along, it's kind of hand in hand with IoT. And with that, obviously, there's a ton of different companies you can buy IoT devices from. So that's kind of another big defining characteristic is, there's not just like a few providers. So I already touched on some of this stuff, but edge computing versus cloud computing. So obviously edge computing is distributed, whereas cloud computing is more centralized into bigger data centers. Edge computing, I already mentioned, has, heterogeneity, many different providers. Anyone can, start making IoT devices or start making, have like a micro data center with a few servers and call it like an edge node. Whereas with cloud computing, there's really only three and maybe a few more, but the big three cloud computing providers. So next I have low latency, which we've already talked about, whereas with cloud computing, depending on how far away you are, you might have variable latency. Edge computing is local, whereas cloud computing can be regional or global. And then edge computing, there's usually limited like storage and compute capacity per each edge node, whereas with cloud computing, it's basically unlimited because these data centers are really big and there's tons of servers. So that's one difference there. So I'm going to give 3 use case examples that I just think were very interesting that I found. The first one is mobile users. So obviously, like as apps start getting more advanced, start doing stuff like machine learning, like Google Translate is using machine learning, or like facial recognition or whatever. And then also obviously multiplayer games, they need really low latency, basically like real-time computing. And also just like with ML, it's just very computationally heavy. So the physical size of a device, like a little mobile phone, does constrain that computing ability and like storage ability. It is getting better, but obviously you're not going to be able to have like the phone size is going to stop getting bigger eventually. So that's always going to be a bit constrained. So oftentimes these devices, these apps use the cloud to do a lot of that computing, and you can use edge networks, mobile edge networks, to make that latency a lot better. So I've already talked about MEX a little bit, basically the low latency, and also the ability to handle users moving around and going from one node to another. You don't want like a 5-second gap in service when you move from like using one node to now you're closer to another. So obviously you have to come up with a system to handle that. And then the performance cost trade-off, which is how many servers to place and where to put them to maximize the user performance while also not spending too much money on servers that you don't actually need. Use case 2, intelligence logistics centers. So this is basically just an unmanned distribution warehouse where a network of sensors and robots is actually managing, taking cargo, moving it around, organizing it, and then basically the storage and retrieval of goods. So this is, I always just think Amazon warehouse. If you've ever seen any of those videos of the robots kind of moving stuff around, that is an intelligence logistics center. So these are becoming more common, and large centers, obviously, if you think about the round trip that it might take for a single robot that just needs to know, maybe it needs to know that some new cargo was just dropped off and it needs to move over there and pick up a box. If it had to go all the way, make an entire round trip all the way to the cloud data center to get that information and then wait for that, the answer or, the information to come back, that's might be too long. Whereas if you just had a local edge node right there that could just do that quick little, send that quick little message, it would be basically real time, and that can actually save power consumption as well, because then you don't have robots sitting around idling when they don't need to be. So I also have on there about fog layers versus edge layers. I'll talk a little bit more about that later, but fog layers are kind of a level above what they consider like edge devices, whereas edge devices are just there to handle like quick local decisions, like the example I just gave. Whereas the fog layer kind of handles the main I/O with the centralized cloud network, and also some more like if there needs to be any computation or like data abstraction performed. Over there on the right is an example from a research paper where they actually figured out like the optimal placement of edge nodes and fog nodes for a data center that they were researching. So use case 3, security and emergency alerting. I wanted to give this one because I feel like home security systems are one of the most common edge network use cases that people might have heard of. So if you get like say some kind of computer camera to monitor your house, there'll probably be some kind of sign up where you have to sign up and pay a certain amount per month to use that provider's cloud network, which is most likely an edge network. And in fact, that camera is probably an edge device as well. It might be doing some, a little bit of pre-processing or figuring out, maybe caching stuff locally and then sending it up to the cloud every few hours or once a day or something. So that's one example. And then I say here, because edge nodes are more context and location aware, it's actually, if an incident occurs, they actually can very quickly respond to that event, as opposed to, obviously, like I've already talked about, the latency making a round trip to the centralized cloud, so that can be good. It can quickly contact people that should be contacted, the people whose house has been broken into, or various emergency services. And then I have over there on the right this example of the Emergency Help Alert Mobile Cloud, which is an app that was proposed by researchers where basically there's just a few buttons on the app and people can just click the button and it'll immediately reach out to, there you see like a micro data center, which is a fog or edge node, that then contacts the emergency services and family members that they've predefined. So I thought that was a pretty cool example. So now I'm going to talk a little bit about different technologies. So this is just a overview of edge computing layers. So I've already talked about, this was actually from the Intelligence Logistics Center example. So you have sensing or IoT devices, and then edge devices, which are like maybe very small, like single board computers or individual small servers Fog devices usually have a little bit more, like maybe they have some storage caching, maybe they're like a few servers or VMs, and then there's a gateway, and then they communicate up to the cloud center. So here's some terminology you might hear. Obviously, Internet of Things, IoT, they're just kind of sensors. Usually they don't have a lot of compute power, or like smart home devices or whatnot. And they're often the things that are then hooking into the next level, which is edge devices or nodes. Sometimes I've noticed people use it interchangeably with fog, but really edge devices usually mean either, the IoT device or maybe like a small server or something that's just very close to the edge of the network. Fog node is also, sometimes the same thing as an edge node, but basically it's just a server, a small collection of servers. It's located between the end user and the cloud. So they call that like in the fog. It's not in, in the cloud totally, it's in the fog at the edge of the cloud. So edge node and fog node are kind of, you can think of them as the same thing. Sometimes they're separated into a couple different levels though. So a cloudlet, sometimes also called micro data center, we saw that in one of the previous diagrams. It's a small cloud data center, or sometimes you can, like with Azure Stack Edge, I think, you basically can set up a micro data center within another data center that you're using like a cloudlet. But it has more functionality than like a fog or edge node, but it still exists between your end user and the cloud. So it's probably doing some like I/O with the main cloud, and it's got more storage, it's got more servers available. So it's like a little bit more robust version of a fog node. So this is just like a couple diagrams that show the difference. Obviously with fog node, you'd still need the data center, whereas with a cloudlet, that could act as your data center, and then it could just send the data directly to the cloud. So a couple examples here. So over there, I have a couple like hardware examples. Obviously, these edge nodes are often servers. So Lanner has a server that's has really low latency and high throughput. That's really good for this. And then there's other kinds of boards like Coral. They offer a TPU board, which is specifically it's like a single board computer specifically for neural nets. So that's pretty cool. And it also integrates with the Google IoT API, and it uses TensorFlow, which is a Google ML offering. So that's pretty cool. You can do like pretty intensive neural net ML stuff at the edge of your network, like really close to whatever you're doing, as opposed to going out and using Google's API or whatnot. So it's pretty cool. So cloud provider edge offerings. So all of them pretty much have something. Microsoft Azure, I've already talked a little bit about. Azure Stack Edge, which is where you're basically creating a cloudlet that lives on a physical computer in some data center that's closest to you, or like a sub data center, and you're creating a little cloudlet that you can use use your hook up your like IoT devices to or whatever. Amazon AWS, they have actual devices. I guess that you could consider them IoT devices. I have a picture of one there on the left, but they're computers. They actually have storage, they have processing. So they're little tiny edge nodes, and they're called Snowcone devices, which is kind of cool. Google GCP, I've already mentioned the Cloud IoT API, which can integrate, and you can use it to control different edge devices, like the Coral board or like other Google smart home devices. So current challenges in edge computing. Obviously, there are a lot, and this is a very cutting edge field, so there's a lot of stuff going on, a lot of research happening. I've already mentioned heterogeneity, which can be bad because numerous standards and architectures presents challenges. Programmability, if you're trying to integrate a sensor with a cloud or with an edge network, like how do you know what languages you can use, what protocols it uses for communication, etc. It can just be hard to know. And then if you need to switch it, maybe you need to change everything about what you were doing because now you're on a different edge network and it uses completely different communication. And obviously integration is really hard when there's no standards. So that's one thing. Extensibility is just how easy it is to add or remove a device from the edge network. Is it easy to just drop another one in if it needs to be extended, or that can be difficult. And then obviously, so isolation, reliability are kind of hand in hand. So this is kind of about just like failure. So if obviously, like usually with an edge node, you have multiple IoT sensors connecting to it, and you have to have it so if one starts erroring out, that doesn't mess up the connection for any of the other sensors. So it has to work regardless of what's going on, like with the IoT devices or the mobile devices that are connecting to it. And then obviously you have to consider failure, recovery, and backup on such a widely distributed network with like so many different nodes. If there's a failure, how are you recovering from that without losing data, obviously. So performance cost trade-off I've already talked about for mobile edge, and that's just about the optimal placement and number of servers to place in the edge network without, spending too much or having not enough, so that you basically should just be using the cloud network, the centralized cloud network, because latency isn't getting improved that much. And so then privacy and security is the last thing, and that basically is just abstracting personal data enough so that you preserve privacy of people, so that obviously like IoT devices collect a lot of personal information. You don't want to be like maybe sending too much of that out into the cloud. So that's often the responsibility of edge devices to kind of abstract that data, but still have it so that it's meaningful. And then obviously lack of universal standards. And so if you're hooking up to an edge network, how do you actually know that that's secure? How do you know that that data that you're sending to it is going to stay secure and private? So all of these are considerations. Thanks for watching. Let me know if you have any questions. You can email me or message me on Teams.